building large autonomous ships for the Navy, and we're building the Port Alpha, which will be the most advanced shipyard anywhere in the world. We're rethinking how we build ships in this country so that we can bring a very critical capability back to our defense industrial base.
Something extraordinary is happening deep inside America's shipyards. A secret new base built not for sailors, but for machines. Dozens of sleek, unmanned warships are being assembled in silence, each designed to fight, decide, and survive without a crew. China's naval strategists are reportedly alarmed, calling it a game changer that could upend the balance at sea. Why is the US hiding it? And what are these robot warships really for? Let's go! The quiet shipyard and the robot fleet. Something extraordinary has been happening on the American coastline, quietly, deliberately, and almost in secret. Out past the old naval yards and container docks, a new kind of shipyard has come alive, one that doesn't build destroyers or submarines, but machines. Here, hulls the size of small yachts glide down assembly lines that look more like car factories than military installations. Robots welding robots, automated cranes lifting modular hulls, and software engineers outnumbering sailors. This isn't the Navy of the past. It's the future, and it's already operating. But what exactly is this place? Who built it? And why is China suddenly so afraid of it? They call it Port Alpha, a purpose-built shipyard designed not for manned vessels, but for fleets of unmanned surface ships. It's not a sprawling base covered in classified bunkers or nuclear reactors. Instead, it's sleek, efficient, and eerily quiet. From the air, you'd see long rectangular hangars, assembly tracks running end to end, and rows of dark grey hulls lined up like chess pieces waiting for deployment. Each vessel is born from a design that values speed over grandeur and quantity over symbolism. Unlike traditional naval yards where a single destroyer can take 7 years and thousands of workers to complete, Port Alpha churns out fully functional ships in weeks. The key lies in its modularity. Every ship shares a standardized core frame that can be equipped with plug-and-play payloads. Instead of custom engineering every sensor, radar, and weapon system, these unmanned vessels are built like smartphones. Swap in a new module, upload new software, and it's ready for a new mission. Components are sourced from commercial suppliers, allowing production to move fast and costs to stay low. Think of it as the naval equivalent of Tesla's Gigafactory, but for autonomous war machines. Legacy shipyards were temples to craftsmanship. Port Alpha is a temple to efficiency. Each bay operates on an assembly line rhythm. One section fabricates hulls, another installs propulsion, while a third integrates AI systems and sensor pods. You could watch a time-lapse of the process and see ships evolve from bare metal to operational drones in a matter of days. The comparison is staggering. While a destroyer like the USS Zumwalt took nearly a decade and over $4 billion to build, some of these autonomous vessels can be manufactured for a fraction of that cost and time. The math alone is terrifying for America's rivals, because in modern warfare, time and numbers matter more than size. Behind this transformation stands a consortium of private defense startups, naval contractors, and public-private partnerships bound together by innovation and urgency. The lead name whispered around defense circles is Saronic, a next-generation defense startup backed by both Silicon Valley capital and Pentagon funding. Saronic's engineers didn't come from naval shipyards. They came from SpaceX, Google, and DARPA projects. Their approach to warfare is algorithmic. They design vessels like software, versioned, iterated, continuously upgraded. Around Saronic orbit a network of partners, legacy shipbuilders that provide certification expertise, classification bodies like the American Bureau of Shipping, ABS, and government agencies buying through flexible OTAS, other transaction authorities, which allow faster prototyping and procurement outside traditional Pentagon red tape. The funding numbers are staggering, even if exact figures remain under wraps. Venture capital has poured in hundreds of millions, while defense contracts have quietly escalated from experimental to operational. Each deal signals a shift. The US military is no longer just buying ships, it's buying a process that can scale. Imagine a future where naval fleets can be replenished as easily as consumer electronics, where new vessels roll off the line every month instead of every decade. That's the scale Port Alpha represents. So what exactly are these robotic warships? They come in a family, each designed for a different role, each small but deadly in its own way. The smallest, nicknamed Spyglass, is just 6 feet long, a fast, stealthy scout designed to skim along coastlines and gather electronic signals. Cheap, expendable, and quiet, it can slip into harbors or follow submarines, feeding live data back to command networks. Then there's Cutlass, about 14 feet long, carrying loitering munitions or small missile pods. It acts like a mobile firing platform, capable of launching precision strikes while swarming in groups to overwhelm defenses. Moving up in size, the Corsair class stretches to 24 feet. A mid-range patrol vessel equipped with towed sonar arrays for submarine detection. It can loiter for days, hunting silently in packs. The Mirage is a 40-foot escort ship, agile and fast at over 35 knots, designed to shadow manned fleets or patrol contested waters. The Cypher class, at 60 feet, focuses on logistics, carrying spare parts, fuel pods, or even functioning as mobile workshops. And towering above them all, the Marauder, a 150-foot unmanned arsenal ship capable of carrying dozens of cruise missiles or acting as a floating base for smaller drones. Each of these ships rewrites the economics of naval warfare. A single Marauder costs less than 1/10 of a conventional frigate, but can carry almost as much firepower. A swarm of Spyglass or Cutlass drones can saturate enemy radar, draw fire, and reveal enemy positions without risking human lives. Together, they form what strategists call distributed maritime operations, a web of semi-autonomous assets working in coordination. Instead of one large vulnerable carrier group, imagine hundreds of robotic ships moving like a digital organism, confusing sensors and forcing adversaries to spend missiles on decoys and ghosts. Mass production changes everything. For decades, navies have been obsessed with building exquisite ships, massive, expensive vessels meant to last 40 years. But in the age of automation and AI, the advantage shifts to whoever can build, deploy, and replace faster. Port Alpha's approach flips the equation. Instead of a handful of billion-dollar ships, the US could field hundreds or even thousands of low-cost, semi-autonomous vessels. It's the same logic that made drones reshape the skies, now applied to the oceans. If you could see a side-by-side timeline, an aircraft carrier taking 10 years to build, versus a robotic warship rolling off the line in weeks, the future becomes obvious. Quantity becomes its own form of quality. In a potential conflict, every week counts, every hull matters, and every delay costs strategic ground. That's why Port Alpha isn't just an experiment. It's a signal to the world that naval warfare is entering an industrial revolution of its own. But this story doesn't end with the assembly line. Because to understand why this base exists and why it has China so alarmed, you have to rewind to the technology, the rivalry, and the quiet arms race unfolding beneath the surface, why this is happening, and what it builds on. What's happening right now beneath the surface of global headlines is nothing short of a revolution in naval power, a discovery so recent and disruptive that it's forcing military planners to rewrite decades of strategy. The United States has quietly proven that it can mass-produce autonomous warships, but the reason it's doing so isn't just technological ambition, it's panic. Because across the Pacific, China's shipyards have been building at a rate the world hasn't seen since World War II. The numbers are shocking, and the implications even more so. how did Beijing gain such a massive lead? And why does the US now believe only robot fleets can close the gap? For years, China has held the world's top spot in shipbuilding, not just for civilian vessels, but for warships, Coast Guard cutters, and even fishing fleets that double as state-sponsored auxiliaries. Its shipyards in Dalian, Shanghai, and Guangzhou operate like industrial cities, running 24 hours a day, 7 days a week. At any given moment, dozens of hulls are under construction, from small patrol boats to massive cruisers like the Type 055 Renhai class, each equipped with over 100 vertical launch cells capable of firing long-range missiles. Unlike the US Navy, which separates its combat fleet from its Coast Guard and merchant marine, China's maritime strategy blurs those boundaries. The same fishing trawler that appears civilian on radar can relay targeting data to destroyers or harass foreign ships in disputed waters. This hybrid force, a mix of Navy, Coast Guard, and maritime militia, gives Beijing overwhelming presence in the South China Sea and near the Taiwan Strait. In naval warfare, presence is power. The side that can put more hulls in contested waters wins the battle for information, control, and attrition. In narrow choke points like the Luzon Strait or the Bashi Channel, where every radar contact matters, China's advantage in ship numbers could flood the zone. Even if only a fraction of its vessels are frontline warships, the sheer density of platforms allows saturation attacks, overwhelming enemy sensors and missiles through volume alone. It's a war of exhaustion, and the US can't simply outbuild China using its traditional shipyards. The cost and time lag are too great. That's why the Pentagon turned to automation, to fight scale with scale, but through machines instead of manpower. The path to this new generation of robotic ships didn't happen overnight. It began almost a decade ago with DARPA's Sea Hunter, an experimental trimaran that looked like a skeletal sailboat crossed with a stealth fighter. It was the first large unmanned surface vessel to navigate the open ocean, cross thousands of miles, and follow international maritime rules entirely on its own. The Sea Hunter wasn't armed, but it proved a crucial point. Autonomy at sea was possible, reliable, and cheaper than expected. Then came follow-ons like Nomar and Defiant, designed by defense contractors in partnership with the Navy's Unmanned Maritime Systems Office. These vessels introduced no manning required architectures, meaning every component, from fuel valves to radar calibration systems, could be remotely managed or automated. They also pioneered modularity, interchangeable sensor masts, mission bays, and propulsion pods that could be swapped in hours instead of weeks. What started as experimental prototypes gradually evolved into a doctrine shift. The Navy began funding not just individual ships, but whole production lines built around autonomous design. The technology had crossed the threshold from laboratory experiment to scalable industry. But hardware is only half the equation. The real transformation lies in how these ships communicate and fight together, through something called the kill web. Traditionally, militaries operated with a linear kill chain: detect, track, target, and engage, each step handled by a specific platform. If that link was broken, the attack failed. The kill web changes everything. It's a decentralized, self-healing network where sensors, shooters, and command nodes constantly share data. If one ship is jammed or destroyed, another instantly takes over. Picture this. A small spyglass drone on the ocean's surface detects an enemy vessel using passive sensors. That data is instantly transmitted through encrypted links to a nearby cutlass, which verifies the target's ID using visual feeds. Simultaneously, a distant marauder receives the target coordinates and readies its launch tubes. A human operator, sitting in a control room thousands of miles away, gives final authorization, and the strike is executed within seconds. No single ship has to carry the entire burden. The web distributes the task, making the network itself the weapon. This approach aligns perfectly with the US Navy's new doctrine of distributed maritime operations, dispersing assets to make them harder to target while keeping them tightly connected through data. The goal is resilience. In an era where electronic warfare, cyber attacks, and hypersonic missiles can disable large ships instantly, spreading capabilities across hundreds of smaller nodes ensures the fleet can keep fighting even under attack. It's chess, not checkers, with robotic pawns and algorithmic coordination. Underpinning this strategy is a complex technology stack that fuses autonomy, sensing, and communication. Each unmanned vessel carries a suite of sensors, radar arrays, electro-optical/infrared cameras, and passive acoustic detectors, all feeding into onboard processors that interpret the environment in real time. Satellite uplinks and high-frequency radios connect them to command networks, while AI-based route planning ensures compliance with maritime traffic laws. Since reliance on GPS makes systems vulnerable to spoofing or jamming, engineers are now testing alternatives like inertial navigation and celestial referencing, allowing vessels to find their way even when satellites go dark. And this is where the real drama begins. Because if the US now has the technology and the motivation, the next question is scale. Can this new model of robotic shipbuilding grow fast enough to offset China's industrial dominance? And perhaps more importantly, how will Beijing respond to a world where America's naval advantage no longer depends on manpower, but on machines, scale, integration, reactions, and the real risks? Turning a prototype fleet into a true naval force is far more complex than just building more ships. It's an industrial, political, and logistical balancing act that touches every layer of the defense ecosystem. Port Alpha might look efficient on paper, but scaling from a few dozen experimental hulls to mass production demands something the US hasn't attempted since the Cold War: a wartime manufacturing tempo. The shipyard must expand capacity for hull fabrication, propulsion systems, and AI integration, while supply chains for advanced composites, specialized chips, and maritime sensors need to be both secure and redundant. Every vessel must pass through classification and certification from the American Bureau of Shipping, ABS, ensuring that automation meets safety and reliability standards. Even if the robots can fight autonomously, the infrastructure around them, docks, maintenance depots, and software update pipelines, requires a human workforce trained in entirely new disciplines. Congressional politics could be the biggest speed bump. Traditional naval programs rely on fixed contracts under the Federal Acquisition Regulation, FAR, which can take years to approve. These new unmanned systems are mostly funded under Flexible Other Transaction Authorities, OTAs, which allow for faster experimentation but lack long-term budget stability. Lawmakers tied to legacy shipbuilding districts are already wary of shifting billions away from destroyers, carriers, and submarine programs that support established contractors. The result is a tug-of-war between innovation and inertia. For this new model to succeed, the Navy will have to prove that a hybrid production approach, with both public and private yards working in parallel, can deliver dozens of unmanned ships per year, each with specialized maintenance hubs and rapid deployment cycles. The vision is not to replace sailors, but to multiply their reach through robotic extensions. The next challenge is integration, making sure these robotic vessels don't just exist, but actually work as part of a fighting fleet. In practice, this means new command structures. The Navy is already forming USVRONs, or unmanned surface vessel squadrons, each designed to operate alongside manned ships in carrier strike groups or amphibious task forces. Instead of captains giving direct orders to crews, they'll coordinate with AI systems and remote operators through secure data links. Operators, often stationed on shore or aboard larger vessels, remain the human decision-makers for lethal actions. Every strike, intercept, or engagement still requires a human-in-the-loop authorization, both for legal and ethical reasons. Yet this setup introduces new kinds of stress. A single operator might oversee a swarm of 20 ships, each feeding real-time data. Managing that cognitive load and trusting machine judgment in life or death moments will require new training pipelines and cultural adaptation across the Navy. Captains who once commanded men must now learn to command algorithms. But if the US is scaling up, China won't just watch, it will counter. Beijing has already begun developing its own autonomous surface and underwater systems, many tailored to interfere with or mimic US drones. Its growing expertise in electronic warfare and GPS jamming could render American USVS temporarily blind or cut them off from command networks. Cyber intrusions are another risk. Hacking an autonomous fleet could turn America's advantage into its greatest vulnerability. Diplomatically, China might exploit grey zone tactics, using dual-use commercial ships or militia vessels to provoke, ram, or shadow US drones, forcing Washington into legally ambiguous standoffs. The risk of escalation is obvious. A misidentified contact in the Taiwan Strait, a hacked navigation signal, a mistaken retaliatory strike, all could ignite conflict in minutes. That leads to the most uncomfortable question of all. What happens when things go wrong? A fleet built on autonomy carries failure modes we've never faced before. A spoofed radar signature could trick an AI into targeting a friendly vessel. A sudden loss of satellite comms could freeze ships mid-operation, turning a coordinated network into a drifting liability. The sea itself remains unpredictable. Storms, corrosion, and salt can degrade sensors and software alike. Each failure isn't just technical, it's legal and political. Who bears responsibility if an autonomous vessel makes a lethal mistake? The programmer, the operator, or the government that deployed it? International law has not caught up with these questions, leaving gaps that adversaries could exploit or manipulate. And so the race continues. Industrial, technological, and strategic. Because if the US truly masters this scale of robotic warfare, it could reset global naval balance for decades. But if it stumbles, politically, technologically, or ethically, the very machines built to preserve stability could accelerate the next great crisis. Thanks for watching. If you enjoyed this, don't forget to like, comment, and subscribe. Click the next video for more exciting content.